Good morning, Miss. My name is Lau Yong Pin. My student ID is 12212013882. Today, I'm gonna to present the topic about deadlock. So, before we go to the practical part, I would like to give some explain to the deadlock. The meaning of deadlock is blocking of a set of process. It is completed for system, resource, or communicated with each other. Besides that, it is permanent and non-efficient solution. So here is the example of the law. A set of block process each holding a resource means that, for example, worker A and worker B, they want to maintain the toilet seat. Worker A is using the plunger and worker B is using the wrench. Waiting to acquire a resource held by another process in the set means that worker A, both of them cannot start to maintain the toilet seat because lack of tools. Worker A is waiting of the wrench and worker B is waiting for the plunger. So now we are going to the question and solution. So the question is, consider a system with 7 processes, P1, P0, P1, P2, P3, P4, P5, and P6. 3 resource type, A, 16 instance, B, 17 instance, and C, 19 instance. So here is the allocation table. Allocation table shows that matrix indicates the number of resources of each type currently allocated to each process. So P0 is A1, B1, C2. P1 is A2, B2, C2. P2 is A4, B4, C1. P3 is A1, B3, C3. P4 is A1, B4, C1. P5 is A2, B0, C1. P6 is A3, B1, C5. So here is the total. So how we get the total is 16 instance A because the question, we get it from the question. For example, A had 16 instance, so we use the 16 to minus all of the allocation of A. So 16 minus 1, 2, 4, 1, 1, 2, 3 and get the answer 2. It is the same way for B and C. B, 16 instance, get from the question to minus all of them 1, 2, 4, 3, 2, 0, 1 and get 2. So C is also 19th instance, so minus 2, 2, 1, 3, 1, 1, 5 and get the answer 4, 2, 2, 4. So the next is max table. Max table show that matrix define the maximum demands of each process. So for P0 is A5, B7, C4. P1 is A4, B8, C5. P2 is A5, B6, C3. P3 is A5, B5, C5. P4 is A9, B4, C1. P5 is A3, B2, C6. P6 is A9, B1, C14. So next, need table. Need table shows that matrix indicates the remaining resource needs of each process. So before we know, we need to know how we need to get the need. The answer is we use the max table to subtract the allocation table. For example, P2. The max for P2 is 563. We subtract it for 4, 1, 5, subtract 4, get 1, 6, subtract 4, get 2, 3, subtract 1, get 2. So the answer is 1, 2, 2. It is the same way for the all process. I will show one more example, P6. P6, the max is 9. The allocation is 3. 9 minus 3, it will get 6 of need. So 1 minus 1, 0. 14 minus 5 will get 9. So the answer is 609, the need for P6. So the next one is the remainder. So how we get the remainder is the answer from here. We use the instant that given from question to minus or the allocation from the table and get the answer. And 224 is the instance. So now we are going to the solution part. Before we start, we need to know the ways to do it. So here, 462 is the need. The need for P0 is 462. We need to follow the sequence from P0, P1, P2. If the need is less or equal to the remainder is true, we need to update the remainder. If it is false, we just ignore it. For example, P0. The need of P0 is 462. And it is less or equal to this one? No, it is false. So we just ignore it and go to the P1. P1 is 263. It is less or equal to this. The remainder is also no, so it is false. We just ignore it and go to the next process, P2. P2, the need of P2 is 122. 122, and it is less or equal to the remainder 224. So it is true. 1 is less to 2, 2 is equal to 2, 2 is less to 4. So it is true. So now we are going to use the allocation of P2. Allocation for P2 is 441. So here also 441. 441 plus the remainder 224 and get the answer, then 665. 2 plus 2, 6. 2 plus 2, 6. 1 plus 4 get 5. So we need to update the latest remainder. So latest remainder for A is 6, B is 6, C is 5. So it is done for the P2. Now we are going to the next process, P3. The need of P3 is 422. It is less or equal to the 65. This one is 224 and this one is 65 because here is outdate. After outdate, we need to use the latest one. So it is less or equal, it is true. 4 is less to 6, 2 is less to 6, and 2 is less to 5. So true. So we need to use the the allocation of P3 to plus the latest remainder. 1 plus 6 get 7, 3 plus 6 gets 9, 3 plus 5 get 8. So here is also outdate it. A7, B9, C8. So done for P3, go to the next P4. 800. 800 less or equal to the latest remainder 798. It is false because although 00 is less to 9 and 8, but the 8 is bigger than the 7. Even though it is only 1, but it is false also. So ignore it and go to the next process, P5. 105, it is the need. Is less to the latest remainder 798. It is true. 1 less to 7, 0 less to 9, 5 less to 8. So we use the allocation of P5 201 to plus the latest remainder. 2 plus 7 get 9, 0 plus 9 get 9, 1 plus 8 get 9. So update it is the same way. 9, A9, B9, C9. So after that, go to the next process, P6. P6, the need is 609. Is less or equal to latest remainder 999. It is true. 6 is less to 9, 0 is less to 9, 9 is equal to 9. It is true. So use the allocation of P6 315 to plus the latest remainder, get 3 plus 9 get 12, 1 plus 9 get 10, 5 plus 9 get 14. Update it, A12, B10, C14. So after done it, go to the next process. Here is P0 because here just now it is false. So now we need to check it one more time whether it is true or false. So the need of P0 for P0 is 462. Now it is less or equal to the latest remainder 12, 10, 14. 4 is less to 12, 6 is less to 10, and 2 is less to 14. So it is true. So now use the allocation of P0 to plus the latest remainder 1 plus 12, 13, 1 plus 10, 11, 12 plus 14, 16. Update it and get A13, B11, C16. So after done P0, go to the P1. P1 because it is also false just now, right? So we need to test it one more time. P1 is 263, is less or equal to the latest remainder, so it is true. And now we are going to use the allocation of P1 222 to plus the latest remainder, and 2 plus 13 get 15. 2 plus 11 get 13, 2 plus 16 get 18. So the latest remainder is A 15, B 13, C 18. So go to the P4. P4 is false, right? So we need to do it one more time also. P4 add 0, 0. So now it is less or equal to the remainder. 8 is less than the 15 and 2 of 0 absolutely is less to 13 and 18. So it is true. We use the allocation of P4 1 for 1 to plus the rest remainder to get 16, 17, 19. So here is the latest remainder. If we want to check whether the answer is correct, we can find from here. If the last step after update it the remainder, it must be same with the question. So A is 16, B 17, C 19. So here is also A 16, B 17, C 19. So we can know that our question is correct. So we should give a conclusion. This should lead to a deadlock with the execution. How we get this is we need to see we need to see the sequence that process is true. So the first one true is P2, P3, P5, P6, P0, P1, and P4. So it is follow the sequence P2, P3, P5, P6, P0, P1, P4. So this is a safe state. So here is the end of my presentation. Thank you.
Hi everyone, my name is Joey. Today I will talk about the topic of deadlock. In this topic, we need to prevent the deadlock occurring in an operating system. What are the methods for handling the deadlock? There are four ways to deal with the deadlocks. For the first one is deadlock prevention. Deadlock prevention strategy focus on structurally eliminating one or more of the four necessary conditions for a deadlock to occur, which is mutual exclusion, go and wait, non-preemption, and circular wait. This strategy involves a specific techniques and policy, such as resource allocation policies, designed to prevent the deadlock by carefully managing resources allocation to process. For the second method, which is deadlock avoidance. Deadlock avoidance involves making decisions dynamically to ensure that the system will not enter to a deadlock state. It can be based on a technique like the use of resource allocation graph or state transition model to determine if a resource required to lead to a safe state or potential deadlock. For the third method, which is deadlock detection. Deadlock detection allows the system to enter a deadlock state and then take action to recover from it. This method involves practically checking the system resource allocation and requesting the process state to identify the deadlock. Once detected, the system can take action such as process termination or resource reallocation to resolve the deadlock. Last but not least, the fourth method is the ignore method. The ignore method implies not taking any action to prevent or resolve the deadlock, this allowing them to occur naturally. This approach is generally not recommended for production systems because it can lead to the resource wastage and the system instability. For the deadlock avoidance, there are two approaches. This is resource allocation danger and process initiation danger. For resource allocation danger, which do not grant an incremental resources required to a process if this allocation might lead to deadlock. And the process initiation danger is to not start a process if its demand might lead to a deadlock. And how do we know that whether the process has enough of resources to execute it? Is by referring to the banker's algorithms. The state of system reflects the current allocation of resources to process. There are two states, which are safe state and unsafe state. For the safe state is one in which there is at least one sequence of resources allocation to process that does not result in a deadlock. Meanwhile, an unsafe state is a state that is not safe, and it might lead the system in a deadlock.
And now I got prepared a question to teach you how to use the banker's algorithm to know that whether this system is safe state or unsafe state. Let us see the question. Consider a system with 7 processes P0, P1, P2, P3, P4, P5, and P6, and 3 resources type, which is A with 80 instances, B 80 instances, C 70 instances. And is the system safe? Use Banker's algorithm to prove it and provide your reason. And now, this table is show you each type of the maximum and the allocation for each process. And what we can do is we can separate it with a maximum one table and the allocation one table so that we will easily to view it. So I already done the allocation table and the max table. And in the allocation table, I also do one column with a total for each type of the resources. For the type A is 17, type B 18, and type C is 17. And now we also need a table called needs table. And here we need to use a formula to calculate the needs, which is maximum minus allocation. For example, for P0, the maximum for A is 1. So 1 will put inside here and minus for the allocation P0A1. So 1 minus 1 equals to 0. And for B, the maximum is 4. And the B allocation is 3. So 4 minus 3 equals to 1. And for the C, the maximum is 6. And allocation is 4. So 6 minus 4 equals to 2. And for the P1 process, for type A, the maximum is 3. And the allocation is 2. So 3 minus 2 equals to 1. And for B, the maximum is 6. Allocation is 3. So 6 minus 3 equals to 3. And for C, the max is 2. And the allocation is 1. So 2 minus 1 equals to 1. And for P2, the maximum is 2 minus the allocation 2. 2 minus 2 equals to 0. And for the B, also the same thing. 2 minus 2 equals to 0. And for C, the maximum is 5. And allocation is 4. 5 minus 4 equals to 1. So the remainder, just using the formula, which is max and minus allocation. So you will get the answer. After that, we also need to prepare a table which is resources available. We also call that remainder table or the balance available. So how to calculate this resources available? The formula is resources available equals to the each type of the resources instances minus the total allocation for each type of the resources. So for the type A, the instances is 18. So 18 minus the allocation of table total A is 17. So 18 minus 17 17 equals to 1. And for B, the instances is 18. 18 minus the total of the allocation table of B is 18. So 18 minus 18 equals to 0. And for C, the instances is 17. So 17 minus the total allocation of the C, also 17. So 17 minus 17 equals to 0. So the result of the allocation table, the result of the resources available is 100. And now we are going to check whether each process has enough of the resources to execute it. So there is a tip. The tip is the process needed is smaller equals to the resources remainder. If it is false, it will go to the next process needs. If true or yes, the resources remainder will be added, which is processes allocation plus the resources remainder. So we will do step by step and start from the process 0. For the process 0, the process needed matrix is 0, 1, 2. It takes from here. Here, 0, 1, 2. So 0, 1, 2 is smaller equals to the resources available, which is 100, and compare it. Is 0 smaller equals to 1? No. Is 1 smaller equals to 0? Sorry. Let me repeat again. Is the 0 smaller equals to 1? Yes. Is 1 smaller equals to 0? No. Is 2 smaller equals to 0? No. So true, false, false is the result is a false. And since it's false, we will go to the next process need. For the next process is P1 and the matrix is 131. It's taking from this need table 1, 3, 1. And the P1 matrix 131 is smaller equals to the resources 100. And since the first process didn't have updated, so still remaining the matrix which is 100. And make a comparison. Is 1 smaller equals to 1? Yes. Is 3 smaller equals to 0? No. Is 1 smaller equals to 0? No. True, false, false. So equal also become false. So if false, we will go to the next process needs, which is P2, and the matrix is 001. Let us check whether it's correct. And absolutely, it's 001. So P2 with a matrix 001, whether it's smaller equals to the resources 100. Let us check it out. Is 0 smaller equals to 1? Yes. Is 0 smaller equals to 0? Yes. Is 1 smaller equals to 0? No. True, true, false also become false. So if false, we will go to the next process need. And the next process is P4 with a matrix is 202. Is 202 smaller equals to the resources 100? 2 smaller equals to 1? No. 0 smaller equals to 0? No. 2 smaller equals to 0? No. So false, true, false also become false. And if false, go to the next process, P5 with the matrix needs 101. And smaller equals to the resources 100 and do a comparison. Is 1 smaller equals to 1? Yes. Is 0 smaller equals to 0? Yes. Is 1 smaller equals to 0? No. True, true, false also become false. And next, we will go to the next process, which is P6. It's the last one, which is a matrix need is 111. 111 smaller equal to R, 100. 1 smaller equals to 0. 1 smaller equals to 1. Yes. 1 smaller equals to 0? No. 1 smaller equals to 0? No. So true, false, false also becomes so. So as we can see that from the process P0 and P6, all the statement is false. So we can make a summary or a conclusion says that this system is unsafe state because all the process needs is larger than the resources remainder, or can say that not enough resources to use, and this shall lead to the system into a deadlock state. Thank you for watching. Thank you.